Just beyond Neptune, a vast frontier of frozen worlds drifts in near-total darkness. This is the Kuiper-belt, a sprawling disk of ancient ice and rock holding secrets from the dawn of our solar system. We are about to journey through 25 of its most perplexing and fascinating objects, from shape-shifting dwarf planets to solitary wanderers on impossible paths. By the end, you will possess a new understanding of the dynamic, mysterious archive orbiting in our own cosmic backyard. What force could fling a world into a lonely, thousand-year orbit, and why does one distant object resemble a cosmic snowman? What do you believe is the greatest mystery waiting for us in the deep, cold dark? Our first destination is a world that looks less like a planet and more like a child's toy, a cosmic snowman drifting in the deep freeze. This is Arrokoth, the most distant and most primitive object ever visited by a spacecraft. When NASA's New Horizons probe raced past it on New Year's Day 2019, it revealed a breathtaking sight, a single body composed of two distinct spheres gently fused together. This bizarre shape is a frozen fossil, a direct snapshot of planetary infancy. It shows us that the building blocks of planets came together not through violent, shattering collisions, but in a slow, graceful dance, a gentle accretion where small snowball-like objects gently merged over eons. Even more puzzling than its shape is its appearance. Arrokoth possesses a strangely smooth surface, largely free of the countless craters that scar most ancient bodies. What process could have erased the evidence of billions of years of impacts? Furthermore, it is blanketed in a uniform layer of reddish material, a mysterious tholin that gives it a distinct rusty hue. This color comes from simple ices like methane being cooked by cosmic radiation over the age of the solar system. But why is the color so consistent? Why does this ancient building block look so pristine and untouched? Arrokoth's serene, unblemished face challenges our ideas of the violent early solar system, suggesting its region remained a quiet, undisturbed nursery for an astonishingly long time. It is a perfectly preserved time capsule, and its very existence raises a profound question. What other primordial secrets are hiding in the faint light of the Kuiper-belt? From the pristine fossil of Arrokoth, we travel inward to a world that refuses to be forgotten. Pluto, once the 9th planet, is now revealed as one of the most vibrant and active worlds in the Kuiper-belt. Its most stunning feature is a vast heart-shaped plain of nitrogen ice known as Sputnik-Planitia. This brilliant white heart is not a static scar, it is a beating, dynamic engine driving Pluto's geology. This frozen plain is a puzzle in itself, a basin so massive it may have altered the entire orientation of the dwarf planet, effectively making it roll over so this heart forever faces its largest moon, Charon. But the true mystery lies beneath the ice, the sheer weight of Sputnik-Planitia and the way it has drawn the world's mass toward it strongly suggests something incredible, a deep, liquid water ocean hidden under a shell of rock and ice. How could an ocean remain unfrozen so far from the sun's warmth? The radioactive decay of rocks deep within Pluto's core may provide just enough heat to keep this global sea liquid, a dark abyss waiting in the perpetual twilight. The surface of the heart is equally baffling. It is not a smooth sheet of ice, but a chaotic landscape of giant polygonal cells. These are not impact craters, they are the visible tops of massive convection currents. Solid blocks of nitrogen ice, warmed from below, slowly rise and fall like a gigantic, sluggish lava lamp, churning the surface over cycles that last hundreds of thousands of years. This means Pluto is not a dead, frozen billiard ball. It is a world with slow-moving glaciers of nitrogen ice and a surface that is constantly, imperceptibly renewing itself. Pluto's demotion forced us to look closer, and what we found was not a simple rock but a complex, living world in the deepest sense, whispering of hidden seas and powered by a heart of churning ice. The discovery of Eris ignited a firestorm that would forever change our map of the solar system. Here was an object not just at the edge of the Kuiper-belt, but seemingly beyond it, and it was ever so slightly more massive than Pluto. Its existence in 2005 forced a profound and difficult question. If Pluto is a planet, then surely Eris must be one too. But if we welcomed Eris, how many other such worlds were waiting to be found? This single, distant point of light triggered a revolution in astronomy, leading directly to the creation of the dwarf planet category and Pluto's controversial reclassification. Eris became the catalyst, the usurper that dethroned a king. Yet the world itself is shrouded in its own profound mysteries. Eris possesses one of the most reflective surfaces in the entire solar system, gleaming like a cosmic beacon. It reflects almost all of the feeble sunlight that reaches it, a property that suggests a surface unlike any other. Astronomers believe it is coated in a glittering blanket of nitrogen and methane ice, a frost so fresh and bright it acts like a perfect mirror. How does this ice remain so pristine so far from the sun? The leading theory is as strange as it is beautiful. Eris follows a highly elongated orbit that takes it on a vast journey lasting more than 550 years. As it swings far out into the deepest cold, its tenuous atmosphere, likely composed of nitrogen and methane gas, does not simply vanish. It freezes solid, falling from the sky as snow and settling evenly across the landscape, creating that brilliant, uniform frost. Then, as Eris makes its rare approach to the sun, some of this ice may briefly sublimate, turning back into a thin, temporary shroud of gas before the long freeze begins again. This cycle of atmospheric collapse and rebirth is a slow, dramatic dance we have never directly observed. The debate, however, continues. While we know Eris is more massive, its exact size compared to Pluto remains a topic of discussion. Is it slightly smaller but much denser, packed with more rock deep inside its core? Or is its composition more similar to Pluto's, a complex mix of ice and stone? Eris, the instigator of cosmic controversy, now holds its secrets close, a brilliant, frozen world whose very discovery reshaped our celestial neighborhood and whose own nature remains an enigma waiting in the dark. Its brilliant white gleam is rivaled only by a world that glows with a deep, rusty red. Meet Makemake, a dwarf planet whose color is just the beginning of its strangeness. Named for a creation deity, this object presents a stark contrast to its more famous neighbors. While Pluto and Eris both possess thin, temporary atmospheres, Makemake stubbornly holds onto nothing. It is a world seemingly frozen in a permanent state of exposure, its surface laid bare to the vacuum of space. This lack of an atmospheric shroud is the first major clue that Makemake is built differently, composed of a different recipe of ices that simply do not vaporize easily, even on its closest approach to the sun. But the deeper mystery is its shape. Most worlds of its size are pulled into nearly perfect spheres by their own gravity, yet Makemake is distinctly elongated, almost egg-shaped. This form tells a dramatic story of its past. It suggests that Makemake is spinning and spinning fast. This rapid rotation has literally stretched the world, fighting against gravity's pull to round it out. This leads to a fascinating puzzle about its interior. Is Makemake a relatively uniform mix of rock and ice, or does it have a dense, rocky core that allows its outer layers to be distorted so easily? Its elongated shape is a permanent record of its rotational history, a fossilized spin from the solar system's violent youth. Perhaps the most stunning revelation about this lonely, egg-shaped world came with the discovery of its tiny companion. After years of searching, astronomers spotted a faint moon, now nicknamed MK2, orbiting Makemake. This moon is incredibly dark, a stark black against its brilliant red parent. Its existence is a profound challenge to our ideas. How did such a small, dark moon form around a bright, fast-spinning world? It seems unlikely to have been a gentle capture of a passing object. Instead, it may be the remnant of a colossal impact billions of years ago, a piece of Makemek's own dark interior blasted into space and left to circle its creator. This tiny, shadowy moon now forces us to question everything we thought we knew about the quiet, peaceful origins of these distant worlds, hinting at a past filled with far more chaos and violence than its serene, red surface lets on. If Makemek's elongated shape seems strange, wait until you meet Haumea, a world spun so fast it has been stretched into the form of a cosmic football. This dwarf planet completes a full rotation in just 4 hours, a dizzying speed that has overcome its own gravity, preventing it from ever settling into a sphere. The result is a unique ellipsoid, a world that is nearly twice as long as it is wide, tumbling through the void like a poorly thrown pass. This incredible spin is the central mystery of Haumea. Where did all this rotational energy come from? The leading theory points to a catastrophic event in the deep past, a colossal impact with another large object. This was not a gentle nudge, but a shattering blow that sent the entire world spinning wildly, a wound from which it has never recovered. The evidence for this violent birth is scattered all around it. Haumea is not alone, it is the patriarch of its own unique family. Astronomers have identified a collection of smaller icy fragments, all sharing a similar composition and orbiting the Sun along the same path. These are not random passers-by, they are the shattered remains of that ancient collision, the debris left over from the moment Haumea was struck. Adding further layers to this story are its 2 small moons, Hioka and Namaka. These are not simply captured rocks, they are believed to be large chunks of Haumea itself, blasted into orbit during the same impact that set their parent spinning. Their presence completes a picture of profound chaos, a dramatic family portrait born from destruction. This entire system, the football-shaped world, its family of icy shards, and its 2 loyal moons, stands as a frozen monument to one of the most violent days in the history of the Kuiper-belt, a day that forged one of the solar system's most bizarre and enduring shapes. While Haumea's chaotic family tells a story of violent collisions, another object tells a tale of profound solitude. Sedna follows a path so extreme it defies easy explanation. Its orbit is a long, lonely ellipse, a journey of isolation lasting roughly 11,000 years. At its closest approach, Sedna remains far beyond Pluto, but then it swings outward, receding into a darkness so complete it borders on interstellar space. It travels thousands of astronomical units from the Sun, a distance where our star would appear as little more than an exceptionally bright point of light, incapable of casting a shadow. This raises the central, haunting question of Sedna's existence. What force could have possibly placed it on such a desolate track? The gentle gravitational tugs from the known giant planets are not enough. They could not have launched Sedna into its present orbit without also eventually pulling it back. Something else, something far more dramatic, must have intervened in the distant past. One compelling theory suggests a close encounter with a sibling. Our Sun was born in a crowded stellar nursery, surrounded by thousands of other newborn stars. What if one of these sibling stars passed dangerously close to our infant solar system? Its gravity could have reached out like a giant's hand, plucking a world like Sedna from its original orbit and flinging it into the deep freeze, a permanent exile written in gravity. Another, even more tantalizing idea points to an unseen presence still lurking in the vast dark. Could an undiscovered planet, a true giant hidden in the far outer solar system, be responsible? This hypothetical world, often called Planet 9, might have a gravitational influence vast enough to shepherd Sedna and other detached objects into their bizarre, looping paths. Sedna, therefore, is more than just a solitary wanderer. It is a celestial clue, a piece of circumstantial evidence pointing toward a hidden chapter in our solar system's history, a chapter that may involve either a long-lost stellar family or a massive, unseen neighbor still waiting to be found. Yet another dwarf planet holds a secret that should not exist. Quaoar, a substantial world about half the size of Pluto, was found to possess something utterly unexpected, a ring. This alone was a marvel, as rings were considered the majestic privilege of giant planets like Saturn. But the true shock was the ring's location. It orbits far outside what is known as the Roche limit. This limit is an invisible boundary, a point where a moon would be torn to shreds by a planet's gravity. Inside this zone, rings can form from the debris of shattered moons. Outside of it, gravity is weaker, and all that debris should have naturally clumped together, coalescing over millions of years into a single, solid moon. Quaoar's ring defies this fundamental rule of celestial mechanics. It exists serenely in a place where our physics insists a moon should be. How can this delicate band of ice and rock particles remain a ring and not a moon? The material seems to be trapped in a state of perpetual adolescence, forever refusing to come together. One theory suggests that the particles themselves are uniquely resilient. Perhaps they are incredibly fluffy and elastic, like frozen snowballs. When they gently collide, they do not stick together to grow, but simply bounce apart, preventing the birth of a new moon. Another, more dynamic idea points to Quaoar's small moon, Quaoar. Its gravitational nudges, however faint, might be just enough to stir up the ring particles, keeping them in a constant state of agitation that inhibits their consolidation. This distant, stable ring is more than a curiosity. It is a direct challenge, a cosmic anomaly that tells us our models of how rings form and survive are incomplete. Quaoar asks us a simple, profound question. What other fundamental rules of the solar system are waiting to be rewritten in the dark, cold silence of the Kuiper-belt? Orcus drifts in a mirror image of Pluto's own path. This dwarf planet is often called the anti-Pluto, a near twin in size and orbital resonance, yet it reveals a character all its own. While Pluto's surface is a complex canvas of nitrogen, methane, and carbon monoxide ices, Orcus presents a far more stark and crystalline face. It is dominated by one primary ingredient, water ice, which blankets its surface in a form so pure it gleams with a brightness that rivals fresh snow. This composition is the first major clue that Orcus formed under different conditions or from different primordial material than its more famous counterpart. Why is this world so singular in its makeup, a frozen ball of nearly pure water in a realm where chemical variety is the norm? The presence of some dark, reddish patches hints at a thin veneer of complex organics, but they do little to obscure the underlying ice. This suggests a world that has been largely geologically quiet, its ancient water ice crust preserved for billions of years, a pristine relic of the early Kuiper-belt. The mystery deepens with the presence of its single, substantial moon, Vanth. This companion is unusually large for a body like Orcus, a size ratio that makes the pair feel more like a binary system than a primary with a mere satellite. Vanth itself is an enigma, presenting a stark visual contrast to its parent. While Orcus shines with bright water ice, Vanth is a dark, grey world, its surface likely rich in carbon-based compounds. How did such a dark moon come to orbit such a bright planet? Their mismatched appearance is a profound puzzle. One compelling theory suggests a violent origin, that Vanth is the remnant of a colossal impact that shattered a previous moon or a passing object, its dark material representing the deeper, carbon-rich interior of that lost body. Another possibility is that Vanth was a lone, dark wanderer captured by Orcus's gravity in the chaotic early solar system. Yet its nearly perfect circular orbit makes a gentle capture seem statistically unlikely, pointing more strongly toward a dramatic, formative collision. The Orcus-Vanth system, this bright and dark duo, stands as a frozen record of a specific, violent moment in time, a unique binary whose very existence challenges our models of how such pairs peacefully coalesced from the primordial disk. What other forgotten collisions shape the serene faces we see today? The deep red of Ixion is a signature color of the distant Kuiper-belt. This dwarf planet candidate glows with a moderate, rusty hue, a shade that speaks of ancient chemistry unfolding in the deep freeze. This reddish tint is not a simple stain, it is the mark of complex organic compounds known as tholins. These are not signs of life, but rather the opposite. They are the products of a slow, relentless bombardment. For billions of years, the faint, weak sunlight that reaches Ixion has been breaking apart the simple molecules on its surface, molecules like methane ice. This solar radiation shatters them, and the fragments slowly, inexorably, recombine into new, more complex and much darker substances. It is a process akin to plastic forming from simpler gases, a natural polymerization that paints these distant worlds in shades of brick and burnt umber. The mystery is not that this happens, but why the specific shade and intensity varies so dramatically from one object to the next. What subtle differences in the original ice or in the intensity of radiation create the unique palette of each frozen world? This leads directly to another profound puzzle, the challenge of truly knowing Ixion from our distant vantage point. We cannot see its shape or directly measure its diameter. Instead, we must rely on a delicate balance of observations, measuring its brightness in visible light and its heat signature in the infrared. The combination of these two tells a story, but it is a story open to interpretation. If Ixion is very dark, then it must be quite large to reflect the amount of light we see. If it is very bright, then it can be smaller. Current estimates place it at a size similar to Orcus, but its true dimensions and its precise reflectivity, its albedo, remain frustratingly uncertain. Is its surface a uniform red plain, or a mottled landscape of bright ice and dark tholin patches? Ixion, like so many of its kin, is a reddish blur in our telescopes, a world whose fundamental properties are still debated, reminding us that the most basic truths of these distant realms are still waiting to be uncovered. Another world spins at a dizzying pace, stretching the very definition of a planet. Varuna completes a full rotation in just under 6 hours, a speed that forces its form into an elongated ellipsoid, a cosmic egg tumbling through the void. This rapid spin, reminiscent of Haumea, immediately raises the question of its origin. Was it born from a similarly violent, shattering impact that set it whirling, or did it accumulate its spin through a different, more gentle process? The answer may lie not just in its shape, but in its surprising lightness. Varuna possesses an exceptionally low density, a figure so low it challenges our image of a solid world. This suggests that Varuna is not a single, monolithic ball of rock and ice. Instead, it is likely a rubble pile object, a loose collection of countless smaller rocks and icy fragments, all held together by nothing more than their own feeble gravity. Imagine a gigantic, irregular snowball, packed just tightly enough to maintain its form, but with vast empty spaces and voids within its structure. This fragile construction explains its elongated shape perfectly, as its weak gravitational hold is easily overcome by the centrifugal force of its own rapid spin. Its surface adds another layer to the mystery. Varuna is remarkably dark, covered in a layer of complex, dark organic material that hides its underlying composition. Yet beneath this sooty blanket, spectroscopic hints reveal the presence of water ice. How does a world presumably made of water ice become so dark? The relentless bombardment of cosmic radiation over billions of years has likely processed its surface ices into a tar-like substance, a deep coating that tells a story of immense age and exposure. Varuna, then, is a world of contradictions, a fast-spinning ellipsoid that is both fragile and ancient, a dark-surfaced object with a watery heart. Its very existence underscores the stunning diversity of the Kuiper-belt, a realm where worlds can be dense and solid, or barely held together collections of rubble, each with a unique story written in its spin and its shade. 2000 MS4 is a giant hiding in plain sight. It ranks among the largest known objects in the entire Kuiper-belt, a world so substantial it is a candidate for dwarf planet status, and yet it reveals almost nothing about itself. Through our most powerful telescopes, it appears as little more than a faint, steady point of light, a star-like pinprick that offers no hints of mountains, valleys, or cracks. Its surface seems profoundly, unnervingly featureless. This lack of visible detail is a mystery in itself. Is its terrain so uniformly smooth and homogeneous that no features cast a discernible shadow? Or is it so uniformly dark and matte that its topography is simply lost in the gloom? The prevailing theory points toward the latter, suggesting its surface is coated in a deep, global layer of dark organic gunk, a thick blanket of tholins created over eons of radiation bombardment. This would make it incredibly non-reflective, a dark charcoal ball absorbing most of the feeble sunlight that reaches it. But why is it so dark when other similarly sized worlds like Pluto or Eris possess brilliantly reflective patches of ice? The answer may lie in its profound stillness. Unlike active worlds with shifting ice sheets or possible cryovolcanoes that refresh their surfaces, 2000 MS4 appears to be utterly geologically dead. Its ancient dark crust has likely been sitting undisturbed for billions of years, allowing radiation to process every last bit of surface ice into a complex dark tar. Adding to the enigma is what is not there, a moon. Almost every other large Kuiper-belt object has at least one companion, a telltale sign of a violent past involving collisions or captures. The absence of any detected moon around this giant is statistically strange and deeply telling. It suggests this world may have formed through a uniquely gentle process, or that it has, against all odds, avoided the dramatic gravitational interactions that gifted its neighbors with satellites. 2000 MS4 stands as a silent, dark sentinel, a reminder that size alone does not guarantee intrigue, and that some of the belt's biggest secrets are kept by the worlds that say the least. Another world shatters the familiar pattern of a planet with a tiny moon. Salacia and its companion Actaea are not a primary and a satellite, they are a true binary pair, two worlds locked in an intimate gravitational dance. Their sizes are remarkably similar, with Actaea being nearly a third as large as Salacia itself. This unusual size ratio blurs the line between moon and partner, creating a system that feels more like a pair of cosmic twins than a parent and child. They orbit each other at a surprisingly close distance, completing a full circuit in just over 5 Earth days. This proximity is the first clue to their bizarre nature, hinting at a gravitational relationship that is both delicate and powerful. But the true mystery of this pair lies not in their orbit, but in what they are made of. When astronomers calculated their combined mass and volume, they arrived at a startling conclusion: an extremely low density. This figure is so low it defies a simple explanation of solid ice and rock. The unavoidable implication is that both Salacia and Actaea are not solid spheres. Instead, they must be incredibly porous, like gigantic, fragile snowballs or cosmic sponges. They are likely rubble pile objects, collections of icy fragments with vast empty gaps and voids between them, making them far fluffier and less substantial than they appear. How could such a delicate binary system have formed and survived for billions of years? A gentle, slow accretion of two separate bodies seems unlikely to result in such a close, stable pair. The evidence points strongly toward a dramatic origin, a colossal, glancing impact between two larger primordial bodies in the early Kuiper-belt. This impact would not have been a destructive smash, but a creative brush, a sideswipe that shattered both objects into clouds of debris. From this chaotic spray of ice and rock, the two largest fragments, Salacia and Actaea, gently coalesced nearby, their weak gravity pulling them together into this tight, enduring partnership. Their high porosity is a direct relic of that violent birth, a permanent record of a time when they were not solid worlds but loose aggregations of rubble. This fragile binary pair offers us a unique laboratory. They teach us that the building blocks of the solar system could assemble in ways we are only beginning to understand, not just through gentle mergers or catastrophic breaks, but through a complex choreography of impact and reaccretion, creating delicate, porous worlds that have danced together since the very beginning. These worlds are the quiet elders of the Kuiper-belt. Far from the orbital chaos of others, the cold classicals drift on serene, circular paths, nearly flat against the plane of the solar system. They are the pristine fossils of the protoplanetary disk, the original cloud of gas and dust from which all planets formed. Having never been scattered by Neptune's gravity or stirred by major collisions, they have remained in their original, placid orbits for 4.5 billion years. They are cosmic time capsules perfectly preserved in the deep freeze. Their surfaces tell a consistent and puzzling story, a uniform, deep red color that blankets these objects like a cosmic stain. This is not the random splotching of impacts or geological activity. This is a primordial paint job, the result of solar and cosmic radiation slowly cooking the simplest ices like methane and water into complex, reddish organic compounds called tholins. The mystery is not just the color itself, but its astonishing consistency. Why are these specific objects so uniformly red, while their dynamically excited cousins show more varied hues? The answer points to their profound antiquity and stillness. They have been sitting in the same quiet neighborhood, baking under the same faint starlight for eons, their surfaces processing into this identical rusty shade without disruption. This unblemished red crust is a direct signature of an untouched environment, a chemical clock that started ticking at the dawn of the solar system and has never been reset. Perhaps the most defining mystery of the cold classicals, however, is their social nature. A remarkably high percentage of them are not alone. They exist as binary pairs, two worlds of nearly equal size orbiting a common center of gravity. These are not the typical planet and moon arrangements born from violent impacts. These are gentle doubles, partners that appear to have formed together peacefully from a local cloud of material, a frozen waltz that has continued uninterrupted since their birth. How did so many of these fragile binaries form and survive? In the crowded early disk, gentle collisions and gravitational nudges would have been common, allowing small pebbles to gently coalesce into pairs rather than single bodies. Their enduring partnership is a direct, living fossil of that gentle accretion process. When we look at a cold classical binary, we are not looking at a shattered family like Haumea's. We are looking at the solar system's original blueprint, a preserved moment of peaceful planetary birth, a pair of primordial twins still holding hands after all this time. What other secrets of our own Earth's formation are locked within their silent, red-faced dance? While the cold classicals represent a preserved past, other objects tell a story of violent exile. The scattered disk is a population of gravitational refugees, worlds flung onto wild, unpredictable paths by the giant planets. Their orbits are not serene circles but extreme ellipses, often tilted dramatically out of the solar system's flat plane. Two prime examples of these scattered disk objects are 2000 E170 and 2000 OJ67. These are not peaceful elders, they are survivors of a celestial upheaval that reshaped the entire outer solar system. Their highly eccentric and inclined orbits are the permanent scars of that ancient gravitational violence. The leading theory for their origin points to a dramatic era known as the Late Heavy Bombardment, a time when the giant planets, particularly Neptune, migrated outward. As these planets moved, their immense gravity acted like a cosmic slingshot, hurling countless icy bodies from the inner Kuiper-belt into the distant, chaotic realm of the scattered disk. These objects did not form in their current wild orbits. They were brutally evicted from their original homes. This violent past has left a profound mark on their very nature. Unlike the uniformly red cold classicals, the surfaces of scattered disk objects show a far wider range of colors, from neutral grays to moderate reds. Why the difference? Their dynamic history subjected them to far more varied environments and potentially more impacts. Being flung through different regions of space exposed their surfaces to different levels of radiation, creating a mottled and less consistent chemical history. Their journeys may have even brought them periodically closer to the Sun, triggering temporary atmospheric activity that could have refreshed or altered their crusts, erasing the primordial red paint found on their undisturbed cousins. The violence may have also reached deep into their cores. The gravitational shocks of being scattered could have generated internal heat through tidal forces, potentially melting their interiors and differentiating their structure, separating rock from ice. This means a scattered disk object is not a simple, primitive lump. It could be a geologically complex world with a layered history, its very interior shaped by the same gravitational trauma that defined its path. These gravitational refugees are more than just wanderers. They are active records of the solar system's most turbulent era. Their wild orbits are not random. They are a detailed fossil map of the gravitational forces that sculpted our planetary neighborhood billions of years ago. What other stories of cosmic eviction are written in the chaotic paths of these distant exiles? But what about the countless other frozen worlds New Horizons glimpsed from afar? One such object, officially designated 2014 MU69, offered a tantalizing puzzle even without a close encounter. While Arrokoth received a stunning portrait, this neighboring Kuiper-belt object was studied through a more indirect yet brilliant method, a stellar occultation. Astronomers patiently watched as 2014 MU69 passed directly in front of a distant star, causing the star's light to briefly wink out. The precise timing of that disappearance and reappearance allowed scientists to trace the object's silhouette against the starry backdrop. The shape they inferred was deeply strange, a highly elongated or even bifurcated form, a potential cosmic peanut or a pair of close-knit spheres. This immediately invites a comparison to Arrokoth. Are we looking at another binary contact object, a second fossilized snowman? Or is its shape something entirely different, a stretched and twisted fragment from the solar system's dawn? Its estimated size adds to the intrigue, suggesting it is significantly smaller than Arrokoth, perhaps only about 20 or 30 kilometers across. This places it among the vast population of smaller building blocks that never grew into dwarf planets. How many of these smaller bodies share this bizarre clover-like shape? The prevalence of such forms would strongly suggest that gentle mergers were the dominant construction method for all sizes of Kuiper-belt objects, not just the large ones. A close-up view of 2014 MU69 would be revolutionary. We could see if its surface is as smooth and unblemished as Arrokoth's, indicating a similarly quiet history, or if it is scarred and cratered, a veteran of a more violent past. We could analyze the color and composition of its crust, searching for clues about the original distribution of ices in this region. Is its reddish hue identical to Arrokoth's, or does it tell a different chemical story? This single, faint point of light represents an entire class of unexplored worlds. Its mysterious silhouette is a powerful reminder that Arrokoth is not a singular oddity, but perhaps the first example of a common architectural style in the Kuiper-belt, a style of gentle accretion we are only beginning to comprehend. What other shapes, what other silent duos are waiting in the dark for their moment to be truly seen? Its color is a deeper, richer red than almost anything else in the Kuiper-belt, a shade that stands out starkly against the more common rusty tints of its neighbors. This is the red matter object, a world whose spectral signature reads like a chemical fire alarm. While most Kuiper-belt objects are painted in tholins, this one is steeped in them, its surface saturated with complex hydrocarbons to an extreme degree. The central mystery is not just the presence of these compounds, but their staggering concentration. What specific recipe of ices and radiation could produce such a profound and uniform crimson? The answer likely lies in an almost unimaginable span of time and stillness. This object has probably been orbiting in the same quiet, cold region for the entire history of the solar system, a perfect laboratory for slow-motion chemistry. The process is a relentless, patient bombardment. For billions of years, the faint trickle of solar ultraviolet light and cosmic rays has been striking its surface, which is likely rich in simple ices like methane. This radiation acts like a tiny hammer, breaking the bonds in these methane molecules. The fragments, carbon and hydrogen atoms, are left in an excited, reactive state. They drift and collide, slowly reassembling into new, much larger and more complex molecules. These are the tholins, a tarry, reddish gunk that is essentially a primitive plastic. On most worlds, this process might be interrupted. A collision could churn up fresh, clean ice from below. Geological activity could resurface the terrain. But the red matter object appears to be utterly inert, a fossilized billiard ball with no internal heat, no moons to stir it, and a location serene enough to avoid catastrophic impacts. Its surface has simply been cooking, slowly and evenly, for 4.5 billion years. The radiation has had all the time it needs to process every available molecule of ice into the darkest, most complex hydrocarbons possible. Its unique spectral fingerprint is therefore not a sign of strange ingredients, but of perfect, undisturbed conditions. It represents the ultimate end product of space weathering, a world that has reached the final stage of its chemical evolution, painted in the deepest shade of red the cosmos can produce. What other elemental extremes are hiding on these ancient, unspoiled canvases? Some binary pairs in the Kuiper-belt waltz in serene circles, but others move to a far more chaotic rhythm. One mysterious pair follows a wildly elliptical orbit, a path where the two components swing dramatically close before hurtling far apart in a long, looping dance. This is not the gentle embrace of the cold classical binaries. It is a tempestuous relationship, a gravitational tango that seems to defy the quiet origins we expect from this distant region. The very existence of such a strained orbit is a profound puzzle. How did this system achieve its lopsided configuration without being torn apart? A gentle co-formation from a single cloud of debris should have resulted in a nearly circular orbit, the natural outcome of two bodies peacefully coalescing together. This strange, stretched ellipse points to a history of violence and interference. The most compelling theory suggests a dramatic gravitational encounter with a third, unseen object. Billions of years ago, this binary pair may have been sailing on a calm, circular path when a much larger world, perhaps a dwarf planet, passed dangerously close. The intruder's gravity would have acted like a massive hand, giving the binary a sharp gravitational kick. This kick did not break the pair apart, but it fundamentally altered their dance, stretching their once circular orbit into the extreme ellipse we see today. The fact that they remained bound together at all is a testament to the strength of their gravitational bond, surviving a celestial near miss that could have sent them flying independently into the void. Another, more radical possibility is that this binary did not form peacefully at all. Perhaps it is the product of a violent capture. In the crowded early Kuiper-belt, two solitary objects may have crossed paths and through a complex three-body interaction with a passerby, found themselves snared in each other's gravity, locking into this awkward, lopsided embrace from the very beginning. This single, strangely orbiting pair forces us to reconsider the narrative of a placid Kuiper-belt. It is a clear sign that chaos and gravitational mischief were not confined to the scattered disk. Even in the more stable regions, the histories of these frozen worlds can be marked by close calls and dramatic interventions, their unique orbits serving as permanent records of forgotten encounters in the deep, dark past. Deep in the belt, an object of middling size holds a secret about planetary growth. This Kuiper-belt object is a true missing link, not quite large enough to be a dwarf planet, yet far more substantial than the smaller building blocks around it. Its size places it directly in a mysterious transitional category, a bridge between two distinct classes of worlds, the central puzzle is not its orbit but its very interior. Is this world a geologically complex body, differentiated into distinct layers like a miniature Earth, or is it a primordial lump, a homogeneous mixture of rock and ice from the solar system's earliest days? The answer to that single question would rewrite our understanding of how planets are built. If this object is differentiated, it means it once had a hot, active interior. The heat of its own formation, perhaps from the radioactive decay of short-lived isotopes or the energy of countless small impacts, was sufficient to melt its core. Heavy elements like rock and metal would have sunk to the center, while lighter ices like water and methane floated upward to form a mantle and crust. This process of separation is the first, crucial step in the birth of a true planet. It would mean that even these mid-sized worlds underwent profound internal change, becoming miniature, layered worlds in their own right. But if its interior is a uniform, jumbled mix that tells a completely different story, it would suggest this object formed slowly and gently, never accumulating enough heat to cook its ingredients. It would be a frozen lump of the original protoplanetary disk, a time capsule preserving the primordial recipe of ice and dust that once swirled around our infant sun. How can we possibly know what lies beneath its frozen crust? Astronomers search for subtle clues. They measure its density, a figure that requires knowing both its mass and its exact size. A high density points toward a rocky, differentiated core. A low density suggests a more ice-rich and likely homogeneous composition. They also look for evidence of past surface renewal. If fresh, clean water ice is visible on its surface, it could be a sign that its interior once churned, bringing deep material up to the crust, a telltale sign of a differentiated past. This missing link object is therefore more than just another frozen world. It is a single data point that holds immense power, a key that could unlock the mystery of when and how the chaotic rubble of the early solar system began to organize itself into the layered planets we know today. Was planetary differentiation a common, almost inevitable process, or a rare event reserved only for the largest and luckiest of worlds? The silent, frozen answer waits in the dark. Chaotic motion is not confined to orbits alone. One particular Kuiper-belt object takes unpredictability to a deeply personal level, tumbling through space in a state of constant, disorienting rotation. Unlike Earth or Pluto, which spin neatly around a single, stable axis like a well-thrown top, this world rotates around multiple axes at once. It wobbles, it flips, it rolls end over end in a dizzying celestial dance. Astronomers call this a non-principal axis rotation, but a simpler term is a tumble. The object is not so much spinning as it is flailing through the void. The central mystery is what could have thrown its rotation into such disarray. The most obvious culprit is a violent impact, a recent glancing blow from another object, even a relatively small one, could have struck it off kilter, imparting a complex spin that it has not yet been able to stabilize. Yet another possibility involves gravity. A close gravitational encounter with a massive neighbor, perhaps during the solar system's chaotic youth, could have gravitationally torqued the object, nudging it into this wobbly, unstable state without a direct collision. This tumbling has profound consequences for the world itself. Imagine the surface of this object. One moment, a particular patch of ground is facing the distant sun, soaking up what little warmth and light it can offer. Hours or days later, that same patch is plunged into the deep freeze of shadow, only to be heated again from a completely different angle as the object continues its tumble. This creates wildly erratic surface temperatures with no consistent day-night cycle. There is no permanent frozen pole or sun-baked equator. The entire surface is subjected to a chaotic, unpredictable pattern of heating and cooling. How does this affect its geology? Any volatile ices on the surface, like nitrogen or methane, would struggle to find stability. They might sublimate from one area when it briefly turns sunward, only to refreeze somewhere else when that region rotates into darkness. This could create a bizarre, ever-shifting landscape of temporary frosts and evaporating deposits, a world whose very skin is in constant, thermally induced flux. This tumbling relic is a stark reminder that stability is a privilege even for a world. Its chaotic dance is a frozen record of a past disturbance, a wound that never healed, leaving it forever turning and twisting in the dark, a silent testament to the violence that shaped even the smallest corners of our solar system. Its color is a deeper, richer red than almost anything else in the Kuiper belt, a shade that stands out starkly against the more common rusty tints of its neighbors. This is the red matter object, a world whose spectral signature reads like a chemical fire alarm. While most Kuiper belt objects are painted in tholins, this one is steeped in them, its surface saturated with complex hydrocarbons to an extreme degree. The central mystery is not just the presence of these compounds, but their staggering concentration. What specific recipe of ices and radiation could produce such a profound and uniform crimson? The answer likely lies in an almost unimaginable span of time and stillness. This object has probably been orbiting in the same quiet, cold region for the entire history of the solar system, a perfect laboratory for slow-motion chemistry. The process is a relentless, patient bombardment. For billions of years, the faint trickle of solar ultraviolet light and cosmic rays has been striking its surface, which is likely rich in simple ices like methane. This radiation acts like a tiny hammer, breaking the bonds in these methane molecules. The fragments, carbon and hydrogen atoms, are left in an excited, reactive state. They drift and collide, slowly reassembling into new, much larger and more complex molecules. These are the tholins, a tarry, reddish gunk that is essentially a primitive plastic. On most worlds, this process might be interrupted. A collision could churn up fresh, clean ice from below. Geological activity could resurface the terrain. But the red matter object appears to be utterly inert, a fossilized billiard ball with no internal heat, no moons to stir it, and a location serene enough to avoid catastrophic impact. Its surface has simply been cooking, slowly and evenly, for 4.5 billion years. The radiation has had all the time it needs to process every available molecule of ice into the darkest, most complex hydrocarbons possible. Its unique spectral fingerprint is therefore not a sign of strange ingredients, but of perfect, undisturbed conditions. It represents the ultimate end product of space weathering, a world that has reached the final stage of its chemical evolution, painted in the deepest shade of red the cosmos can produce. What other elemental extremes are hiding on these ancient, unspoiled canvases? A fresh scar glows faintly in the perpetual twilight. This particular Kuiper belt object shows a startling spectral signature, one of water ice so clean and bright it screams of recent exposure. In a realm where every surface is expected to be ancient and darkly stained, this brilliant white patch is an anomaly. It is the unmistakable sign of a wound, a place where something has violently stripped away the billions of years of reddish tholin gunk to reveal the pristine, frozen heart beneath. The central mystery is not that an impact occurred, but that we can see its ghostly aftermath at all. How could such a fresh feature persist in this deep freeze? The environment here is not conducive to rapid change. A crater on Earth is eroded by wind and rain in mere centuries. A crater on the Moon can last for eons. But here, in the Kuiper belt, the forces of erosion are almost non-existent. There is no wind, no liquid water, no tectonic activity to rub the scar away. The primary eroding force is the same thing that created the dark crust in the first place, the slow, relentless drizzle of cosmic radiation. This radiation will eventually process the newly exposed water ice, breaking its molecules apart and recombining them into new, dark compounds, repainting the bright scar with that familiar rusty red. The fact that the scar is still visibly bright and icy tells us something profound. The disruption happened recently, but what does recently mean on a cosmic scale? The repainting process is incredibly slow. That bright patch of water ice could be 10 million years old, or perhaps even 100 million. In the context of the solar system's 4.5 billion year history, that is the blink of an eye. We are looking at a geological event that is essentially current, a fleeting moment of violence preserved in slow motion. The nature of the disruption itself is the greater puzzle. Was it a straightforward impact from a rogue piece of space rock? The energy required to blast away such a large area of surface material would have been tremendous, potentially coming close to shattering the entire world. Or could the cause be something stirring from within? Could we be seeing the evidence of a cryovolcanic eruption? Perhaps a buildup of internal heat from the decay of radioactive elements or the lingering warmth of its formation forced a slushy mixture of water, ammonia, and methane up through a fissure in the crust, painting the landscape with a bright, fresh layer of slush that then instantly froze solid in the vacuum of space. This object forces us to confront a dynamic reality. The Kuiper-belt is not a museum where all the exhibits are frozen in place. It is a living landscape still being shaped by occasional, powerful events. This single, bright scar is a time capsule within a time capsule, a fleeting window into the ongoing geological life of the solar system's final frontier. How many other worlds are hiding similar, recent wounds beneath their serene, dark faces? Its orbit is a path of pure defiance, tilted at a steep angle to the flat disk where the planets peacefully circle. This is an inclination misfit, a Kuiper-belt object that refuses to follow the rules, climbing high above the solar system's plane before plunging back down in a solitary loop. Its existence is a direct challenge to the image of a calm, orderly disk of frozen debris. How did this one world get thrown so dramatically off track? The answer lies in gravitational chaos, a reminder that the early solar system was a far more violent and dynamic shooting gallery than we once believed. This object was almost certainly not born with this wild inclination. The primordial cloud of dust and gas that formed our solar system was a flat, spinning disk, and all the objects coalescing from it naturally inherited that same general alignment. For a world to achieve such a steep tilt, it had to be given a powerful gravitational kick, a nudge that literally knocked it out of its original placid orbit. One compelling suspect is Neptune. During the era of planetary migration, the giant planets reshuffled the entire outer solar system. As Neptune moved outward, its immense gravity would have acted like a cosmic paddle, striking countless icy bodies and sending them careening onto new paths. Some were flung inward, others outward, and a few, like this misfit, were pitched high above the plane, their orbits tilted like a hat knocked askew. But Neptune's influence might not be the whole story. Another, more dramatic possibility involves a visitor from beyond our solar system. Our sun was born in a cluster with thousands of other stars, and in that crowded stellar nursery, close encounters would have been common. What if another star passed near our infant planetary system? The gravity of this sibling star could have reached into the Kuiper-belt, plucking objects from their orderly orbits and tossing them onto these highly inclined paths, a permanent scar from a long-lost stellar neighbor. This single misfit is not an oddity, it is a clue. Its steeply tilted orbit is a fossilized record of a specific gravitational event billions of years ago. When we map the inclinations of many such objects, a pattern begins to emerge. They are not randomly tilted, but often cluster in specific orbital families, each family potentially the legacy of a different disturbance, a different chapter of gravitational violence. This misfit forces us to see the Kuiper-belt not as a simple, flat ring, but as a thick, puffed-up disk, its structure sculpted by ancient chaos. Every steeply inclined orbit is a question, asking us what giant force, what passing stranger, was responsible for its lonely, elevated path. Our final object travels a path so alien it seems to belong to another star. This potential interloper, a world like Sedna or 2012 VP 113, follows an orbit of profound isolation, a slender ellipse that spends most of its lifetime in the desolate gloom, thousands of times farther from the Sun than Earth. Its journey is so vast and lonely that it exists in a gravitational no-man's land, far beyond the direct influence of Neptune or the other giant planets. This radical path is the central clue to its bizarre origin. How did it get there? The gentle gravitational nudges from the known planets are simply not powerful enough to explain such an extreme and stable orbit. Something else, something far more dramatic, must have placed it on this track. One of the most captivating theories suggests this world is not a native of our solar system at all, but a captured exoplanetesimal, a primordial building block from another star. Our Sun was born in a dense cluster alongside thousands of other stellar siblings. In that crowded nursery, the infant planetary systems would have been close enough to gravitationally interact. It is possible that this object forming around a different star was gently stripped away during a close stellar passage and subsequently captured by our Sun's gravity. It would be a cosmic orphan adopted by our solar system and placed into its deep freeze orbit billions of years ago. Another possibility is that it was once a resident of our own outer disk, but was flung outward by the gravitational hand of an unseen giant, the hypothetical planet 9. Yet its orbit is so detached, so pristine, that many scientists lean toward the interstellar capture theory. The implications of this are staggering. If one object was captured, then countless others could have been too. The exchange of material between stellar systems may not be a rare event, but a fundamental part of galactic evolution. Our solar system could be filled with such frozen refugees, each a silent ambassador from a long-lost stellar sibling. This means the primordial ingredients of other stars, the very stuff of alien planetary systems, could be orbiting right here in our own cosmic backyard. The Kuiper-belt might not be a closed family album, but a library of stolen books, each world a volume from a different stellar collection. As our journey ends, we are left with a profound new perspective. The Kuiper-belt is far more than a ring of ancient ice. It is a dynamic, chaotic, and deeply mysterious frontier, a place where the past is perfectly preserved, the present is actively unfolding, and the very origins of our cosmic neighborhood are still being decoded in the faint, cold light of the distant sun. These countless puzzles and paradoxes lead us to the grand, unresolved inquiries that define the frontier itself. After meeting shape-shifting worlds and gravitational refugees, we are left staring into the dark, asking what it all means on the grandest scale. Just how many of these frozen worlds are actually out there? Our current census is like mapping a continent by the light of a single candle. We have catalogued only the very brightest and closest objects. For every Pluto or Eris we find, there are likely thousands of smaller, darker bodies lurking unseen, their combined mass a hidden factor in the solar system's balance. The true size distribution remains a profound unknown. Are there just a handful of large dwarf planets left to find, or are we on the verge of discovering another world rivaling Pluto in size, hidden in an orbital plane we have not yet searched? This directly fuels the hunt for the solar system's most tantalizing ghost, Planet 9. The strange, clustered orbits of extreme objects like Sedna are the primary evidence for this hypothetical giant. Its gravitational influence is the simplest explanation for shepherding these distant worlds into their peculiar paths. But does it truly exist? Is it a rogue planet captured by our Sun, a primordial giant that formed in the deep cold and was never disturbed? Or is the clustering of orbits a statistical illusion, a mirage created by our limited viewpoint? Finding Planet 9, or definitively disproving it, would be one of the most significant astronomical discoveries of our time, rewriting the story of our solar system's formation and its final boundary. Perhaps the most transformative question concerns the hidden interiors of these icy spheres. We now suspect that worlds like Pluto, and possibly even smaller ones, harbor deep, liquid water oceans beneath their frozen shells. How common is this phenomenon? Is a subsurface ocean the rule for mid-sized Kuiper-belt objects rather than the exception? If so, the number of potential habitats for life in our own solar system would expand exponentially. These are not the sun-warmed oceans of Earth, but dark, abyssal seas, potentially kept liquid by the gentle heat of radioactive rocks or the gravitational friction of an orbiting moon. They could be ancient, stable environments isolated for billions of years. The Kuiper-belt, once seen as a deep freeze, may in fact be a sanctuary for countless hidden seas, each a world unto itself, waiting in the perpetual night for a future mission to reveal its secrets. From the chaotic tumbles of ancient worlds to the silent orbits of binary pairs, the Kuiper-belt reveals itself as a realm of breathtaking diversity and profound mystery. These 25 objects are not merely a collection of frozen rocks. They are a living archive, a dynamic frontier where the history of our solar system is written in ice and shadow. We have encountered shape-shifting dwarfs defying gravity, solitary wanderers on paths of impossible exile, and fragile binaries holding hands since the dawn of time. We have seen evidence of hidden oceans, violent collisions, and surfaces painted by the slow, patient brush of cosmic radiation. This is not an empty void. It is a vibrant, evolving landscape, a testament to the chaotic and creative forces that built our cosmic home. The greatest discoveries are still to come, waiting in the faint light at the edge of our vision. As missions like the James Webb Space Telescope turn their gaze toward these distant worlds, they will peel back layers of mystery, revealing new secrets about our origins and the potential for life in the deep, cold dark. This journey belongs to all of us. Share your wonder, follow the discoveries, and let us know which of these enigmatic objects captures your imagination the most. Is it the cosmic snowman Arrokoth, the brilliant usurper Eris, or the lonely wanderer Sedna? The conversation is just beginning, and the next chapter of exploration is ours to write together.